Hello and welcome. This is the next question. This is question number 6 for AQA's AS Physics. This is Unit 1, June 2010, question 6. Quite a big question, okay, but there's a lot of sub-questions in it. It's worth 9 marks, so pretty big bit of paper. Anyway, the first little question says, a semiconducting diode is an example of a non-ohmic component. State what is meant by a non-ohmic component. Well, that's a very, that pisses me off straight away. It sounds far too complex for the actual answer of the question. But the key word I would pick out of all of that is ohmic. And obviously if we know what ohmic means, we know what non-ohmic means. The only word in the whole of AS Physics that relates to some kind of ohmic is ohm, and that is related to Ohm's law. Okay, so let's just recap what Ohm's law was. Ohm's law states that the voltage is directly proportional to the current across a component, providing the physical conditions do not change. In other words, the temperature stays the same. But that goes all the way back to that's just Ohm covering himself so that he's not bothered by superconductivity, which is a totally another topic. Okay, and anyway, we know that just says that therefore the voltage is equal to the current times a constant, which is the resistance. Okay, because obviously resistance doesn't change. And for this, we're just looking at a simple fixed resistor, obviously. So if a component does not follow that the voltage is directly proportional to the current, okay, therefore it does not have a constant of proportionality. In other words, this resistance, it does have resistance. We're not saying it doesn't have resistance, we're just saying it's not a constant value. Okay? So therefore, yeah, that's all you would say for 6A is not a constant resistance value. If you were not sure about, if you knew Ohm's law was P equals IR, but you weren't, you weren't sure. That's a stupid thing to forget. You weren't sure what the voltage was proportional to in Ohm's law. Was it proportional to the current, or was it proportional to the resistance? Well, hopefully you get the idea that it's proportional to the current because the resistance is constant. Okay, for a fixed resistor. But if you didn't know that and you just forgot on that, because it's quite easy to do, you thought the voltage was proportional to the resistance with the constant of the current. Okay, it almost makes sense. And you say, well, it doesn't have a constant current. Then, if you're not so sure about it, what I would put, and this is another answer I put for 6A, I don't think it specifies it on the mark scheme, but I don't see why it wouldn't allow it. One of the other answers I put is it's a component which does not follow Ohm's law, which is I think perfectly acceptable, because it has the same principle, because Ohm's law says that the voltage is directly proportional to the current. Even you're just saying a component which does not follow that. Well, it's the same thing as that it does not have constant resistance. Okay, so to be sure, in them kind of questions, I would do what it said in the exam mark scheme, which was that it does not have a constant resistance. But I don't see why it says that you couldn't have that component doesn't follow Ohm's law. My only thoughts are it's a little bit vague. It doesn't say it doesn't have a constant resistance. It doesn't say that explicitly. But as I said, if you're not sure, I would just put that, just in case, because that's better than definitely putting it doesn't have a constant current, because that doesn't make sense. Okay, so if you weren't sure, I would have put that it doesn't follow Ohm's law. Okay, and hopefully you got that from the ohmic. Anything that says ohmic, okay, is to do with Ohm's law. Okay, they will never just bring up something you haven't learned. So you just think, what does it? If you get a question like that and it's about ohmic conductors or anything, for example, and you're not sure what it means, you just have to think, well, what have I learned that is similar to that? Because that's what they will do in the exam. They will try and trip you up in terms of, you do all the past papers and then walk into the exam, it looks like a topic you've never done before. Well, it is, but it's just manipulated in a way that it looks like a totally new topic. You just have to think, well, what have I done that looks like this, that I can apply to this question, that is mentioned a few things that I already know about, and then try and manipulate that topic and put it into the context of the question. But as I said, maybe that's just me being an arse. Okay, so anyway, 6b. We've got a nice little diagram here. Just have a go at drawing it. Okay, so on the x-axis we've got potential difference, and on the y-axis we've got current. Okay, now you should know straight away, well, the equation we'll be using there is V equals IR, and obviously the gradient is the current over the potential difference. So if you use V equals IR, then obviously what we've got there is 1 over the resistance as the gradient, okay? So anyway, I'm just trying to pick a different pen. Okay, so we've got a filament lamp is also an example of a non-ohmic conductor. So in other words, it doesn't have constant resistance. That's what it's saying there. And we've got this kind of, sketch on the axis below, the example of a current voltage characteristic for a filament lamp. Well, as we said, the gradient is 1 over the resistance, so if the resistance is changing, this gradient will change. I know it's 1 over the resistance, but it'll still, if you know, it'll still be increasing and decreasing, okay? So, is it 1 over the resistance? B equals IR. Yeah, anyway, so, something like that. Alright, so that's what you would draw on for 6b. Now, the reason for that, it's just a case of learning that. There will never, a filament lamp will never have anything other than that. Okay. So that's one of the graphs you just should know, really. Okay. So the next part, 6b part 1. Okay. 6b part 2 says state with reference the current voltage characteristic you have drawn and how the resistance of the lamp changes as its potential difference across its terminals changes. Okay, so it's not give too much away about that graph. It's just saying explain the gradient and why it looks like it does. Okay, but you just need to say about the fact that the resistance increases as the current increases, and therefore you have to state the reason for that. So basically, you have to show what this graph is showing. Okay, and therefore what it is and why it is showing that. Okay. So as I said, you just need to explain about the fact that resistance is increasing. Resistance increases as potential difference increases, and you could go both ways with that. I mean, that's probably not the best wording. You just say as the potential difference gets more extreme, then the gradient will get more extreme as well. In other words, if the potential difference increases, the resistance will increase. If the potential difference decreases, then the resistance will also increase, because we've got a steepening gradient there. Okay? But as I said, you could just put that. Right, anyway, and you just explain why. You just say, this is because the lamp, the filament lamp has a positive temperature coefficient, and I'm not going to emphasise what that means, but it just means the resistance increases, the temperature increases. Positive temperature coefficient. So that's just the relationship between temperature and resistance. Okay, so positive, direct. If it's negative, it's an inverse relationship. Okay. Anyway, go on to 6c now. So 6c says a filament lamp has a power rating of 36 watts when there is a potential difference across terminals of 12 volts. So it's asking us to calculate the resistance of the filament lamp when the potential difference across its terminals is 12 volts. Okay, so we just write down everything we know so far. So we're told that the power of the lamp is 36 watts, so that's equal to the power. Okay, we know that the potential difference, okay, so PD, is equal to 12 volts. Okay, and we want to know the resistance across the filament lamp when the potential difference is 12 volts. Okay, so is there any equation that links P, V and R? Well, no. The only equations that we link, so let's see what is there. So there's no equation that links all three together. So the power, the potential difference, and the resistance. And you could go, well, we've got two equations for power. We've either got P equals IV, or because V equals IR, we can sub in that power is equal to the current times the resistance squared. Sorry, no, squared. Power is the current squared times resistance. Sorry. Okay, so, but the fact is, if we were to use that P is equal to I squared R, well, we don't know the current. So, therefore, we couldn't work out the resistance either. We've got two unknowns. So, what essentially we have to do is combine these two equations. In other words, we have to work out the current first, then we can sub it into the second equation. Okay? So, we've got the equation that links power, potential difference, is P is equal to IV. So, that allows us to work out the current. So, we're saying 36 watts is equal to the current times 12 volts. So, therefore, quite clearly, the current is equal to 3 amps. Okay, and if the current is equal to 3 amps, we can now put that in our known values. So the current is equal to 3 amps. Okay, so now we've got the power, the potential difference, and the current. Okay, so totally up to you what you do now. You could use V equals IR. Okay, because we've got the potential difference, we've got the current, and we just need to know the resistance. Or you could use P equals I squared R. And you sub in your values. But I'm going to use V equals IR because it's easier. You don't have to do any square rooting business. Or, well, you don't have to do any square rooting actually, it's totally up to you. Okay, whether you use P is equal to I squared R or V is equal to IR. As I said, I'm lazy, so I'm just going to use V equals IR. So 12 volts is equal to the current, 3 amps, times the resistance. Okay, quite clearly, therefore the resistance is equal to 4 ohms. Okay, so it has to give it in. Yep. Okay. It gives you the unit anyway, so just simply put 4 in the answer box. Okay. Is there any other parts of this question? Okay. No. 6C part 2 says a student predicts that the potential difference across the bulb. If the potential difference across the bulb is reduced to 6 volts, their power rating of the bulb would now be 9 watts. State and explain how in practice the power rating will be slightly different from this value. Okay, so let's just think about this. If we lower the potential difference, the current, if we have the same, if we're not changing the current, but all we're changing is the potential difference. Okay, therefore this should result in a lower resistance. Another way of thinking about it is, you know, the positive temperature coefficient, this graph thing. If we lower the potential difference, therefore the gradient gets a bit less, so therefore the resistance will decrease. Okay, hence the power, because power is equal to I squared R, therefore the power would also decrease. Hopefully that makes a little bit of sense. As I said, I couldn't really bother right now because it's only a little bit of an explanation. So sorry I keep having to look at my sheet. I've just I printed it off, so instead of keep turning back to my computer, I just thought I'd waste a bit more of your time looking down at a sheet. Okay, so any questions about that question? Please let me know. As I said, I've gone through everything I think I can. If you do want me to go about this graph again, because I don't think I've given it the best explanation, please let me know and we'll try and go through it in the comments again, or do another video on it if you're really that asked about it. But anyway, thanks for watching. I will see you in the next video, which will be the last question, question 7.